All right. So, hi and welcome everyone. My name is Harshit Rehan, and today I'm gonna be talking about the topic uh, that was for my term paper, which is software development and optimization for parallel computing systems. So, before we get started, I just hope that all of you are doing well and that you're not going crazy in quarantine, unlike me. Okay. So let's get started. Yeah. So we'll just quickly go through the outline for this presentation. So first we'll have a brief introduction this mostly consists of stuff that we've already gone through in the class, but we'll go through it still once more so that everybody's on the same page um, before we start the main topics of the presentation, which will be the first thing would be we'll discuss in brief about some of the steps, the most generic steps that are taken to convert sequential code to parallel code or just to write parallel code in general. And then we'll discuss about some types of analyses that are performed on sequential code to extract some important vital information that allows us to convert that code from sequential to parallel. And then we'll go through some of the different approaches which are taken to achieve parallelization. And then we discuss some really key state of the art tools for parallelization. So some of which have been around for quite a while, but some of them are like really recent, and they provide really good performance. And then we also talk about some of the recent research advances in this field. So there's like a couple of topics which use machine learning and some meta heuristics to sort of automate this process and decrease the level of human and developer involvement. And then the conclusion, of course. All right. So let's get started with the introduction. So, so as we know that our computing needs, they are ever growing. They'll always grow. In the next 10 years, we will need much faster computers than what we have right now. That's that's a fact of life at this point of time. So, and the advancements made in hardware and the hardware engineers, they have really kept up with this increase with this increase in the growing computing needs. And this has been done with the introduction of multi-core and many-core machines. And so it's said that the free lunch of software developers is over, which means that software developers now they just cannot like sit back with their hands folded and say that uh, I'm doing the best I can. This code just cannot run faster than this on this machine. Now, software developers have had to adapt and change their entire programming paradigm and their entire structure to come up with novel ways and to new ways to utilize these powerful machines which offer a lot of speed with with the multi-core and many-core fashion. Yeah, multi-core and many-core architecture. So when you're writing a new parallel application, then then if you think about, like I mentioned today, that the hardware advances today, they they have CPUs with multiple cores. One machine can have multiple CPUs, which is many cores, and then we have GPU, and then FPGA. FPGA is no, one second. Okay, so when you're writing new applications, so like I said earlier, hardware advances have made it possible to to utilize the different processing units that are in the machine. uh, they can be CPU with multiple cores, or more than one CPU in one machine, and then GPU with multiple cores, and then FPGAs, which are field programmable gate arrays. They also provide a processing unit which can help to execute parallel code. And so systems such as these, they are known as heterogeneous systems. Heterogeneous because we can utilize more than one processing unit, sort of. So if we're just utilizing CPUs and multi-core CPUs, then that's a homogeneous system. If we're utilizing just the GPU and just the multiple cores in GPU, that's also a homogeneous system. But now we have we are pulling in together different processing units, so that's known as a heterogeneous system. So now, with this kind of system, there are also a lot of issues. Like the programming becomes complex. Obviously, if there are so many processing units, you at each step while you're writing code, you're gonna have to keep in mind that you have these many available units. So you're gonna have to make sure that you take advantage of all of those. And then also, if all of these programming units are running, then obviously it's gonna increase the energy consumption, definitely. And then again, while programming, the number of parameters that you need to consider is like it just increases a lot. Like for example, the number of CPUs, the number of GPUs, what's the clock rate of the CPU, what's the clock rate of the GPU, the memory, what level of caching is there in each core of the CPU, in each core of the GPU, L1 cache registers. You have to think of all of that stuff so that you're able to actually optimally utilize these features, and also the architecture of the CPU, the GPU, and the feed programmable gate array. So this heterogeneous systems in itself, it becomes like a really hard problem. And so that's one of the reasons that why when you convert like sequential code to parallel code, then it's it's not advisable to run it on a heterogeneous system, because then first the code conversion is in itself a really daunting task, and then after that, mapping and scheduling different parallel units to different threads to run on different processing unit is also becomes a difficult thing. So that's why for the rest of my of our discussion, we stick to homogeneous systems, which means that uh, CPU, multiple CPUs with multiple cores, but just we'll talk about just CPUs. Okay, and then the most common scenario these days is converting the legacy applications which have been written for over 10, 15 years, and which have been just evolving for the past 10 years, but they have all been written sequentially, and now they need to be parallelized. So so in order to utilize the hardware promises, we need to parallelize them, because a sequential code written a legacy application which has been written quite a while ago sequentially, and now if you're running it on today's modern machines which offer so much more in terms of performance, then definitely if you do not parallelize them, then you are totally underutilizing the hardware's capabilities. And now this task of converting sequential to parallel, it's actually more difficult than writing a new parallel code, because if you think of it, that if you're trying to write new parallel code, then the first thing you would do is you would study a parallel programming framework like OpenMP, MPI. You would study those frameworks, and you will get used to them. You'll get comfortable in using them, and then you'll just start programming. But in this case, you don't do that. You just have a huge code base of hundreds and thousands of lines, and now you need to and it's written in entirely in a sequential fashion, and now you need to identify that which parts of that we can run parallelly, and then do that. So that's a really difficult task. Yeah. And then also energy utilization is also a key concern, and another thing that needs to be kept in mind is load balancing on CPUs. Yeah, we've basically gone through this already in class, I think. Yeah. Okay, so let's discuss the steps towards parallelization, which is up next. So the most general steps would be to perform static analysis of code, and then the dynamic analysis, and then with help of these two analyses, we identify the key units of code that can execute concurrently or basically parallelly, excuse me. And then we refactor the code or basically change the code so that it is actually converted to parallel code now. So after identifying the key units, we now actually change the code so that it can be executed parallelly. And then the last step, and one of the most crucial steps, would be to map the parallel code to the available CPU cores. Because and it's really important, because if you think about that, even if you like spend hours and hours, and a lot of manpower, a lot of time cost and all that, just to convert the code from sequential to parallel. But then if you are not mapping, if you're not threading your code properly, if you're not mapping the parallel units that can execute concurrently to proper cores, and the scheduling is just a mess, then basically all that effort has gone to waste, and you still can't utilize the power, the the capability of of the multi cores. Okay, so over here we saw that static analysis, and then there's dynamic analysis. So now we're gonna go through. So there are basically two types of analyses, and these analyses don't only pertain to parallel programming. These are like the most general. These are in general. These are known as static and dynamic analysis, and they are done for a lot of other reasons as well. Just for example, to identify bugs in code or to identify some security threats or security leaks. Okay, but that doesn't concern us. So we'll stick with static and dynamic analysis in respect to parallelization. Okay, so the first question is why should we analyze code? Well, if you think about it, you need to analyze code because if you have 100,000 lines of code, this huge code base, and you're supposed to convert, and it's all sequential, and you're supposed to convert it from sequential to parallel. You cannot go through it line by line. I mean, your human brain simply cannot comprehend all of that code. So that's why you need to analyze it using sophisticated tools that give you important information about the code. So that's why we use the tools. And then again, like I said, static analysis and dynamic analysis. Okay, so static analysis basically means that you analyze the software before actually executing it. That you have a block of code, and you put it into a tool, a static analysis tool, and then it spits out some information related to the tool. That's it. That's the analysis. And this allows the developers to identify the most common and most obvious parallel patterns in code. Yeah. So like some like the most basic level of loop parallelization, and the most basic levels of the data flow and data dependencies that can be analyzed pretty well, and basically very fast with static analysis. So one of the key, I would say, attractions of static analysis is that it's pretty fast. There's like really less overhead. So the steps would be, let's just quickly go through them. So the step would be that first first you first you select the source code that the developer needs to parallelize. Then the source code is passed by a tool which will analyze the code, and then it also refactors the code into concurrent executable modules. So the tool has identified that these code snippets can be executed parallelly, and it has refactored them for you so that it can actually execute parallelly now. And then there's some additional tools. They also analyze the modules for safety, and potential deadlocks and race conditions. And then and then finally, when all of this is done, the developer is given with a preview of the analysis, like sort of the result of the analysis, documentation, if if you'd like to think of it like that. And then and then if the developer approves, that's it, and then the code is refactored, and then it is run concurrently now. Yeah. And so there are a lot of static analysis tools available in the market now. Some of the most common ones are CompuWare, Apache Eaters, and Intel Advisor. And now, although static analysis looks like really promising and really easy, it has some limitations, actually got a lot of limitations. So the first thing is that a lot of data dependencies, excuse me, they don't arise until runtime. So so until you compile the code and actually execute it, you won't even know that some sort of data dependency can exist in the code. So that's a potential limitation. And then same is true for deadlocks and race conditions, because until the code is running, you never know. Maybe midway execution there can be a deadlock that analysis couldn't figure out. So that's a limitation. But the advantage is that there is like very low overhead cost for this. Okay, so let's talk about dynamic analysis. Dynamic analysis is performed on a computer program by actually executing it on a processor. So static analysis, we didn't execute the code, we just had the code and we fed it into a tool. With dynamic analysis, we actually execute the code and then the tool looks at the code's behavior and how it's executing and what's happening. So again, this enables developers to identify a lot of errors that can identify due to parallelism like deadlocks and race conditions. Obviously, this makes sense. If when the code is executing, if there's a deadlock, then the tool will be able to identify that there's been a deadlock. So the developer will now have that information that because of these execution steps, there has been a deadlock. So you need to fix that in order to make it a successful parallel code. And yeah, it basically gives a really deep level understanding of parallelism. And again, this is much better than performing only static analysis. Typically, you always perform both of them, static and dynamic. So we're just going through them one by one. So again, it's much better than performing only static analysis, which doesn't happen in practice quite often. Yeah. Okay. So and this allows the developer to look for even greater degrees of parallelism, such as loop level, and then program flow dependencies, data flow dependencies, and most importantly, task dependencies. So that's the most important part of dynamic analysis, which static analysis cannot figure out on its own. So task dependency, so task A and task B cannot execute without the result of task A, or something like that. If there's a dependency between tasks, or if task B in its execution is calling task A, so that sort of thing. And then dynamic analysis also has this aspect called profiling, which enables the developer to it basically enables the developer to attain a lot of useful insights of the program, such as what's the instruction scheduling, that in which order they call, and the branching algorithms, that at which point is the flow forking, and stuff like that, function calls, frequency and duration and stuff like that. So profiling is basically, perhaps I would say, the most important uh, piece of information that you get after doing the dynamic analysis. It's a really important aspect of dynamic analysis, profiling. Okay, and then dynamic analysis, most common tools would be Parasoft, JTest, Dell Thread Checker, and Capo. Okay, and then so if you think about it, then after doing the static and dynamic analysis, we refactored the code, we've identified parallelism and all that. Again, then the next part, the most important part, would be this mapping parallel code to the available multi-core processors. Because if this isn't done properly, then all that time and effort that's been put into refactoring the code is just gone to waste right here. That's all. Yeah, so that needs to be done really carefully. Okay, so let's go through the parallelization, excuse me, parallelization approaches. So basically, the classification is done by the degree of the human or developer involvement, and there are three broad categories: automatic, semi-automatic, and then parallel languages and APIs. So in automatic parallelization, effort is low, developer dependency is also low, and the degree of parallelization is also low. On the other hand, in semi-automatic, effort is moderate, because semi-automatic, and developer dependency is also moderate, and parallelization is moderate. Moderate over here, basically, it just means that compared to automatic, it's more. So comparatively it's more than automatic, so it's moderate. But I wouldn't even classify it as moderate. It's still low, basically. Yeah. And then the main thing is parallel languages and APIs. Yeah, if you're writing fresh code in a parallel language using some parallel programming frameworks and APIs, languages such as Haskell, Silk, and OpenMP framework or MPI framework, then definitely effort will be high. You'll have to sit down. You'll have to learn the entire framework, learn the language, learn the functions to fully utilize it. The developer dependency is also very high, but the degree of finalization that you get is very high. Yeah, so it's very high because again, comparatively, yeah, it's really high compared to the above two. So let's just quickly go through automatic parallelization. So yeah, so this basically involves next to zero effort and input from the developer. So basically all the developer does is takes the code, shoves it into a tool, and then the tool spits out um, parallel code. That's all. So it works as a black box in which the program source code is fed in the application, which is mostly a compiler. Yeah, this is an important point, which is mostly a compiler. Okay. And automatic parallelization usually only performs static analysis because it also does refactoring and also a lot of other stuff. So the static analysis is low overhead and it's faster. So that's why it performs static analysis of the code and it mostly checks for data dependencies and that's all. And then it automatically converts the program to a parallel program. Like I said, it's like a black box. The smart analysis engine that's working in the background does the entire work. Yep. Okay. So and yeah, developer dependency is extremely low. So that's pretty much it about automatic parallelization. And then the drawbacks again. First of all, only static analysis has a drawbacks which we've already discussed. Degree of finalization is also very low, and this focuses more on the code semantics and not the logic of the code because with static analysis you actually really can't get the logic of the code really well. You can't understand that really well, and then the results of such tools they are heavily dependent on the programmer's actual coding style. If like two different programmers code the same problem and then one of them writes a really efficient program, then the results of automatic validation for the better program would be better, obviously, because the coding style is better and it depends highly on the coding style. And then yeah, a lot of parallelization opportunities are missed, and then these tools are dependent on the language of the source code, of course. So they basically need to parse the entire source code. So one tool can what every tool has to be dependent on the language of the source code. So if somebody has created a tool for C, then it can only work on C. Yeah, exactly, because it's not platform independent. Again, next we have semi-automatic. So this does not provide end-to-end sequential to parallel conversion. So they require some essential input from the developer, which could be in the form of loop parallelization opportunities where the developer annotates or includes some information and then they explicitly mark the variables which are global and which of them are shared so that the data dependencies are are fully checked, and then forking instances are also marked and stuff like that. So the information is derived from dynamic analysis of the source code, and which is again not available if you only do static. Advantages is that the degree of finalization is higher compared to automatic finalization tools, and it utilizes both dynamic and static analysis. So best of both the worlds. And the disadvantages, user effort is comparatively greater, and it's highly dependent on the developer as well. Developer has to put in some time and g- get that information and sort of make changes in the code so that the tool performs better. Okay, so this is the best option that we have: parallel programming languages and APIs. So languages such as C, C++, uh, you know, and Fortran, they are all languages and they have been uh, written sequentially traditionally, and they are used with automatic and semi-automatic tools to achieve parallelization, but it's still not as great as you would want basically for in today's world. So now there are a lot of different APIs and frameworks that are used with these languages, because these languages on their own cannot achieve that. So you have two options: either integrate them with some sort of APIs that increase performance of these languages, or write code in some new language which is totally parallel. And and parallel languages are basically known as functional languages, and we'll get to them in a minute. Yeah. So yeah, so you use them with APIs such as MPI and OpenMP. So it enables developers to convert sequential code written in languages such as C and C++. But even with the use of APIs, they are still limited in the degree of parallelization. So the solution could be to just write code in functional languages which are inherently parallel in themselves. So these languages can be Haskell, Silk, Go. So this enables the developers to write code which is highly parallelized, and it's also surprisingly it's not that difficult to write, because the documentation and they provide written constructs that you can directly import and use them in your code. So that's also a really good point. And the advantages are that they give extremely high degree of parallelization. I mean, this couldn't get any better than this, I guess. Right now, yeah, you have 8 cores. You can concurrently, if you have 8 cores, you can concurrently run 8 threads, and all of that can be configured really quickly using a language such as Haskell, Silk, and Go. But the drawbacks is, of course, again, the developers have to spend hours, hours, not even hours, days, and months maybe, trying to fully understand and learn the language, trying to understand what functionalities do they provide, and to fully utilize it, basically to exploit all the features. So developer dependency and effort required is really high. So that was about parallel programming languages and APIs. So now we'll quickly go through 4 or 5 parallelization tools, and then we'll discuss some of the recent advances. Okay, so Loop Sampler, this is an open source dynamic analysis tools. It focuses on profile-based analysis, and then it identifies potential parallelism inside loops and nested loops. And it has a novel sampling approach which reduces the profiling cost compared to other standard loop analyzers. So this is a really nice tool used these days. Then Alchemist, this is not open source, this is self-paid, and it was developed in 2010. And this is a rated dependency and profiling tool. Again, dynamic analysis profiling tools are like the go-to go-to tools for a lot of developers. They give the best results basically. Yeah, so it's a profiling tool again. So it not only provides loop parallelization, it also provides task level parallelization and level parallelization. And the main feature is that if you remember from class, if you have a look ahead of degree more than 2, then you will not only have write after read conflicts, you can also have write after write or read after read dependencies. So this tool is on its own, it's able to handle those dependencies. And whenever it finds such a dependency, it just refactors the code in itself. So this is also like an automatic parallelization tools, and I would say one of the best ones to be developed. Then Silk, like you mentioned, it's a functional programming language, and it's a parallel programming language. Obviously, inherently it's parallel, and it also has a concurrency platform. And I included it in tools because one of the main features of this is that it helps the developers to utilize a straightforward constructs. So they already have some predefined constructs that you can just import and then use them to run your code. And it also has its own scheduler which takes care of the thread scheduling, and all the issues that we discussed earlier, like parent child process mapping to multi-cores and all that stuff. And Kremlin is a really exciting tool. It's actually a really novel tool, because you usually what tools do, they perform a critical path analysis which gives like the flow of the program from one task to the next, from one task to the next. But in terms of parallel computing, you will think that uh, hierarchical hierarchical path analysis would be better, right? Because you can map parent to child forking and all that those instances. So this is Kremlin is like the first tool which has actually implemented this hierarchical critical path analysis methodology, and the results have been really promising. And there have been a lot of improvements compared to standard CPA. So now HCP is being utilized in a lot of other tools, and this also Kremlin also has an inbuilt OpenMP parallelism planner. So it will not only perform a dynamic analysis and hierarchical critical path analysis and give you the information. It will also produce some skeleton OpenMP code or structure that you can use via this planner that you can sort of use to now refactor your code, and it works on all level of parallelisms like thread, task, instruction. And then par for all is also it's essentially it's a tool. The most common use of this is actually as a compiler for C and Fortran language, and then it implements a script that takes in a C or a Fortran code, and then it parallelizes it parallelizes it on its own. My bad, I don't know. And then it maps it to a parallel OpenMP or CUDA output that can be run with these frameworks. So it has two options. Map the you can either map the C or Fortran sequential code to a parallel OpenMP framework, or to the parallel CUDA framework, and then you can just refactor the code in either of those frameworks and run it. Yeah. And then let's go through the recent advances. So okay, so this is a static analysis tool, and I decided to include this tool because the results of this tool, uh, being a static analysis tool, were really impressive. So I thought that I should include this. So this has been proposed by David Del Rio Astorga et al. In 2016, so which is like really recent. And this focuses on identifying different types of parallelism inside sequential C++ code. It's only for C++ right now. And there are the patterns that I mentioned, which it identifies. There are three of those: pipeline, map, and farm. So pipeline pattern basically it identifies the code segments that would work as a pipeline, like the output of the previous segment would be the input of the next segment. So so you see like a pipeline that, and then map. What map does is it identifies different functions that can execute concurrently on one stream on each data item of the data stream. So like you have five different functions, and then you have a data stream. Then each five of those functions can run concurrently on each item in the data stream. And then the farm pattern would be the opposite of pattern. What this would do is that it will run the same function. It will run the same function on different data items that are available in the stream. So does that does that make sense? So like map would be that different functions each operating on one data item, that's map. And then farm would be one function each operating on, and sorry, one function operating on one data item each. That's it. So the steps, the first thing it would do, it would like identify parallel loops that can be executed parallelly. It's pretty basic for a static analyzer. And then it identifies code segments that can be run in parallel. So identifies loops and other code segments, and then it classifies the identified code segments as pipeline, map, and farm, and then annotates them. It uh, provides some annotations inside the code that allows the developer to see that, okay, so these have been identified, and you can change these. And then the code refactoring is done by OpenMP and Intel's thread building blocks framework. Yeah, and then the developer views the annotations, and then he can either modify and delete them. And if he feels good with the results, he can just commit to them and refactor the code. So this is like the basic working. You have the source code. This part will do loop detection, then feature extraction, and feature extraction includes like checking some arguments for reference kinds, like is it by value or by reference. So this part is basically to identify the parallel to identify the parallelism that exists in the code. and then the flowchart in blue it actually classifies the patterns. It actually classifies the parallel segments into pattern. Like so, suppose like this parallel segment is is of pipeline pattern, and this parallel segment is of map pattern. This parallel segment is of farm pattern. So this is what it does, and it creates annotations, and then the annotated source code is the output over here. And then if you talk about the results, they use Rodina benchmark and NAS parallel benchmarks for evaluation. So these are standard code segments uh, which are in the test column, and these are the number of loops, which doesn't concern us. So basically, what this result is showing, this is PPAT over here says that these patterns have been identified by the PPAT tool, and then these patterns over here have been identified manually by developers. So as you can sorry, as you can see that for the if you look at the first one, PPAD has identified 3 pipeline, 7 farm, and 7 map. On the other hand, manual has identified only, like manually, developer was able to identify only 2 pipeline and 7 farm and 7 map patterns. So you can see for all of these, the results are quite promising. 16, 12, 12 by the tool, and 15, 13, 13 manually, 1, 8, 8, 1, 10, 10. So the results are quite promising. So this is for the Rodina benchmark. This is for the NAS benchmark. And then the next thing that they did is they also compared the execution time of, so like I said earlier in the steps, that it also refactors the code, this tool. So after the developer views the annotation, so these are the annotated code. After developer views these annotations and the developer commits to these annotations, then then the tool will automatically refactor the code for you, for the developer. So this is the comparison of execution time of the refactored code compared to other categories, which I'll just explain. So execution time is over here, and this is again the benchmark code used, B-tree, particle filter. These are from the Rodinia benchmarks, and then so you can see, if you look at B-tree, the sequential code execution time, and then the PPAT execution time and OpenMP. So it's the performance is not worse than OpenMP. And remember that this OpenMP execution has been done manually. So the PPAT execution is done by the tool itself, and then it's being compared to manually refactoring the code, which is a lot more effort and a lot more time spent by the developer. And tool is doing it automatically. So yeah, in most cases, it's almost equal. In most cases, it is equal to the OpenMP manual conversion. So which is a great result. So again, next and the last topic that we look at is a fully automated scheduling technique, which is proposed by Wang et al. So this is a compiler-based fully automated profiling and scheduling technique. What this does is it will map the parallelized code to a multi-core processor, and they basically focus on determining two things. One of them is the number of threads that a program should run in, and the optimal serialization policy. And the most exciting feature is this is platform independent because it's a machine learning technique. So if you have a code in Java, if you have a code in C, if you have a code in Fortran, doesn't matter. Just we can just use this technique, use the models that they've used, and we'll have an optimum scheduling policy and optimum scheduling fully automated. So let's get into this. So the overview is that they use two models. They use one artificial neural net, to create a predictor model which will predict the optimum number of threads for a program. That if I have a program, then the ANN model will give me the number of threads that I should run it in. And the second model is an SVM model, which will choose the scheduling policy from block, cyclic, or dynamic. So dynamic, I'll just try to explain these three policies in one line, if I can. Uh, oh, 40 minutes. Okay, so dynamic scheduling is basically which is done at runtime. It's sort of ad hoc. So yeah, it's done at runtime. There's no fixed structure for it. The scheduler uses its own logic and does this. Cyclic cyclic scheduling is done in such a way that if there are certain jobs that need certain threads that need to be executed again and again and again and again, then they are executed in a cyclic fashion, like ABC, 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 sort of like that. And then the block fashion would be that uh, the all the information that if like one thread is given a long amount of time on one core so that it can actually finish its execution, like the entire block of code is executed without the scheduler pausing that thread, pausing that process, and bringing in another process to execute. That's sort of the block fashion. So these are the types of scheduling. And so over here we'll look at the training quickly. The training data over here, it consists of programs, and it also consists of the speed ups and slowdowns which are achieved with manually trying to refactor the code. And the training data is also a scheduling policy uh, which is being used. So where, as you can see, that this is the training data set. The x vectors are the features which have been extracted, and the features are, there are two basic types: code features, the static instruction count, branch condition, memory access, and there are also dynamic and data features such as L1 cache miss rate and loop count and number of memory access and stuff like that. So X is that. And now for each program, the maximum possible speed up S1 is also given to the neural net. And then to the support vector machine, again the same features as above. And along with that, the optimum scheduling policy to achieve this speed up. To achieve S1, P1 scheduling was used for this X feature. That's the information that's going to the models. And then the training is also very straightforward. We have a new program, so we do profiling of the program and extract those features as the X arrays. Then the artificial neural nets gives us the speed up that's possible, and this speed up that's possible along with the number of threads, along with the number of threads that would result in optimum execution of the program. And then the support vector machine model gives the optimum scheduling policy that should be followed. So we have these parallel configurations which we can set for the program and run. So the results were really promising. So the speed up over here that they are comparing the results to, that speed up has been calculated manually. So and they are taking it as the maximum possible speed up. Okay, and I mean not manually, like experimentally, like on the same program they've tried a lot of different threads and a lot of different policies, and the best they got is the speed up. So yeah, so now we know what the speed up is. We quickly look at the results. So the predictor model was able to achieve 96% of the maximum speed up, of the maximum possible speed up. If the model was able to achieve 96% of that, that's a really great results. And they tested it on two different platforms, Intel and Cell. And and then and then when the same program was uh, refactored and run parallelly in OpenMP's default scheme, then the program was able to achieve 95% speed up on Intel and only 70% on Cell. So the machine learning model was able to achieve 96% on both, and OpenMP's default parallelization scheme was able to achieve 95% on Intel and 70% on Cell. So this is quite an improvement over the default scheme. And the main part is that it's platform independent. If you have these trained models, you can just simply plug in the program and it'll just spit out the optimum number of threads that you need to execute, and the scheduling policy. So conclusion. So we went through these topics, the need for parallelization, the hardware advancements that have been made, and then we also talked about some of the state of the art tools which are available today, and we also looked at some of the most recent advances in parallelization tools. So what I would say is that novel machine learning techniques that we saw, they show some great promise, and they haven't been actually exploited in the field of parallel computing. So that's really a field. So machine learning and parallel computing is a field that that holds great promise, and it should be explored even further, so that the process is more automated, faster, and reduces the developer dependence. So these have been my references, and hope you guys enjoyed and learned something. All right, thank you.